My name is Noah, and this is my Physics Lab 3, in which we were tasked with predicting the mass of a black hole based off the elliptical path of a star orbiting it, and then determining the necessary initial velocity for a spaceship launching off a planet in order to pass close by that black hole without crashing into either the black hole or the planet from which it was launched. And in order to do this, we used two major physics concepts, the first of which being Newton's second law, which states that a change in momentum over a change in time is equal to the net force on an object. And we're going to use this primarily to predict the mass of the black hole given that elliptical path of travel of the star orbiting it. We're also going to use parallel and perpendicular components of force. Every single force can be decomposed into a component parallel to its velocity and a component perpendicular to its velocity, and that can sometimes be very useful for improving the clarity and ease of certain calculations. So we're going to be making use of this as well. Going over to the Glow script where all this code is. For the first half of the lab, I had a random ellipse generated based off of my email, and then I was able to use that ellipse to calculate the mass of the black hole the star was orbiting. So we calculated a change in momentum based off of the changing position, and that change in momentum over the change in time gave us the net force, since change in momentum over change in time is equal to F net over that period of time. And so we were able to use that net force in order to predict the mass of the black hole that it's orbiting, just based off of rearranging the elements of the gravity equation. And as we run that, you can see that we're getting a bunch of slightly different but similar predictions for the mass of that black hole as we travel around. So what this code is going to do is it's going to take all of those guesses and it's going to average them into this number right here, which is our final prediction. So pulling that over into the second part of the lab, I put the mass of the black hole, that number right there, and we use that to model how this system would change over time using the position update formula and the velocity update formula. And then just by experimentation, I found that the y speed of the ship had to be very similar to the y speed of the planet in order to avoid crashing back into the planet after taking off, and the x speed benefited from being very high in the negative direction in order to escape that orbit and get very close to the black hole. So that's going to look like this, and this might not look very close, but it's actually quite close, about the diameter of the Earth. And in this system right here, our spaceship would be our system, and the black hole and the planet would be the surroundings acting on it and pulling on it through gravity. And the initial condition would be that initial velocity that I imparted upon it by launching it very fast in the y direction and very fast in the negative x direction. So going back to our slides in order to discuss the primary differences between our model here and reality. One of the biggest differences would be that I'm using a non-relativistic momentum equation, which might introduce a slight error. And also, the time step for simulation is quite large on the scale of days, which might introduce inaccuracies. As for the what does it mean question, force is what is acting and causing changes in an object, and oftentimes forces can't be directly observed. Much like in the case of this lab, we weren't able to observe a force directly, but we were able to calculate a force by measuring its effects, i.e. its change in momentum of the star. And as for the what if question, if we wanted to send the ship into orbit around the black hole instead of just very close to the black hole, we would need it to give it a very similar velocity to the planet and a very small x velocity to not send it flying. Thank you.